So, hi, my name is Bill Buchanan, and I lead a podcast in the World Leaders in Cryptography series. So, I'm happy to have Vadim Lyubashevsky here with me. Hi.
Hi, hi, Bill.
Uh, So, Vadim is a cryptographer at IBM Research Europe in Zurich. He received his PhD from the University of California, San Diego in 2008. His core research focus is around lattice-based methods and especially in areas of practical lattice encryption, digital signatures, and privacy-preserving primitives. Along with Chris Peiker and Oded Regev, he published a classic paper entitled On Ideal Lattices and Learning with Errors over Rings, which has been used as a foundation for lattice methods within post-quantum cryptography. Vadim has worked in many areas of cryptography, including zero-knowledge proofs, blind signatures, and multi-party computation. So, what's your current role and what does a typical day involve for you?
So I'm now a research scientist in IBM Research in Zurich, and my day is basically what almost what one would do in academia. I do research, I read papers, I supervise students. So it's really very similar to university, but less teaching and committee work. Sometimes, of course, we're called in to meet with clients who would like to understand some of the research that we do, if they're more interested in the theoretical parts, things that we do to design things. So they call us in and we educate the client. Sometimes we help internally with IBM products. Sometimes different groups, for example, would like if they want to make something quantum safe, they ask us, how would you do it? And can you do a mock-up for us? So this is something we do, but really it's very similar to academia, at least for our group.
It's great, yeah. So I suppose it's very much like a research professor type role where you wouldn't have so much teaching. Obviously, in an academic role, you might have some teaching and admin responsibilities. So you've got the best of
Mhm.
really doing research and maybe interacting with the research students. I must admit, IBM is one of my favorite companies. For a company to be around for over 100 years and still be a world leader and still invest in research is really excellent. So, what's it like to work for IBM and how does that work within your research center in Zurich?
I mean, I've been there for almost 10 years now. I think it's great. I really like it. And I suppose it really depends on the group that you're in, right? So people who are, for example, there's a lot of AI work going on, there's a lot of people at IBM working on building an actual quantum computer. So those are very sort of goal-oriented things. This is the goal, right? Whereas in our group, of course, we had the goal, we were working on sort of going to do the standardization of quantum safe. During the standardization process, that was the goal, and that we were doing that. But a lot of it now is now that that's done is we can work on think about what's next. So we are free to think about things that we believe might be useful and practical in like 5 to 10 years time. So there's a lot of leeway in the direction we can follow. Um,
That's great. Yeah.
so that's
And IBM has always been a leader in its field. I mean, it wouldn't still exist if it hadn't invested in R&D and found the products of the future. So if we were to look into uh, uh, into the future, what things do you think IBM will bring forward in the next 10 to 20 years?
well, I mean, of course, AI. Everybody's working on AI, right? So I think you cannot be a big company and say you're not working on AI. So of course, that's going to be something. But I think maybe something that's more unique to IBM is, like I mentioned, trying to really build this quantum computer. They really invested in it very early, so it was quite visionary, I would say. Maybe 10 years ago, they said we're gonna do it. Um, and now we really believe that in about five to 10 years time, it will be something that is. useful, not just something out there that's cool scientifically, but actually useful in practice for modeling nature and applications that we're not yet sure of. And so this actually corresponds quite well to the timeline that the NSA and NIST provided for switching from classical cryptography to quantum safe cryptography. So it seems like that really will be the time that a quantum computer will be built. So these things will match up.
Yeah. And I mean, obviously, we've probably come to the end of Moore's law. So transistors can only go so small, and we can't keep making them even smaller. And it just seems that the next leap in computing is to start to look towards optical circuits and qubits and so on. But we'll come back onto that in the post-quantum. I mean, obviously, what's happening with quantum computers is that it's bringing forth post-quantum cryptography and the opportunities that that will bring. But obviously, there are many risks in that too. So if you go all the way back to your school days, what were you what were you like as a pupil at school?
I liked math. I wouldn't say that I was particularly at the genius level that people around doing cryptography are. Like yeah, even lattice cryptography. There's a lot of people who are like, oh wow, these were they skipped 6 classes and starting college at 13, things like that. So I mean, I liked math. I liked the puzzles. I liked working things out. Um, so yeah, I mean, maybe sort of liking math was more of a because I came to America. So I was born in Ukraine, but I came to America when I was 9, and of course my
Ah,
English was not up to, on par with people who lived there. So naturally, maybe I got slotted into okay, you're going to be doing math. So I said, okay, math I understand. Of course, the system in Ukraine at 9 years old, you were doing more advanced things than the US at 9. And so yeah, I was kind of a little bit ahead already in math and said, okay, that's what I'll continue being good at.
yeah.
So I got
And obviously,
slotted into that. Yeah.
yeah. And obviously the maths that you do at school and university isn't quite the same as the maths you would do in cryptography. So what sparked your interest in cryptography?
Photography, I would say that was somewhat accidental. When I was at university, undergraduate, I was doing a lot of theoretical computer science because I enjoyed that. That was a bit different from math, but similar enough. You required similar type of thinking, I would say. And and so I wanted to continue doing that. I also liked, I think I actually wanted to do game theory, like computational game theory when I went to UC San Diego. But then I ended up with UC San Diego was very strong in cryptography, and I ended up taking a class with Daniele Micciancio, and he was working on cryptography and lattice cryptography. Actually, he was one of the kind of pioneers of that area. And yeah, so I said, okay, well, cryptography has some interesting problems. Let's try to work on that, and that's it. So it was, yeah, there was nothing deep. I know some people say, ah, I cared about privacy and security is dear to my. No, I just kind of lucked
You fell
into that.
into
I
it.
walked into it.
Yeah. So your university career involved, so you went to the University of California, San Diego,
Graduate
and
school.
at the graduate school. So that was you finished there. What was the degree that you did there?
In graduate school, it was computer science.
Computer
So my
science.
thesis was on lattice-based cryptography.
Yeah, excellent.
PhD thesis. Yeah.
So I teach cryptography and RSA is fine. Diffie-Hellman. I can teach discrete logarithms and so on. I can teach how the RSA method work and even El-Gamo. And then I go into elliptic curves and everything is fine. But I'm really worried about how I teach lattice cryptography in the future. So can you give a quick outline of how lattice-based cryptography actually works?
So I would say there's two parts to maybe it's very similar to the way RSA is, right? So there is there's the constructions, right, which require, which, like you said, you can teach in 2 days. You can teach somebody who knows, even someone who doesn't know number theory. You just say, okay, look, here's the stuff, and like, 1 week background in number theory and 1 day RSA, right? But to understand the cryptanalysis of it, that's now you need a degree in mathematics, right? All these number field sieves and things like that. So I would say lattice cryptography, a part of it is very similar. Part of it, you don't even see the lattice. It's just matrix vector multiplication. And actually, after the standards, I wrote a little little tutorial on the standards, the cryptography standards, the digital signature and the encryption scheme that was standardized, Kyber and dilithium. And there you basically don't need to understand what a lattice is unless you care about cryptanalysis. So um, the only thing that makes it a little so, and even the instructions, the high level is very similar to the way El Gamal works, the way the Schnorr signatures work. It's just El Gamal, but with some errors, and it's Schnorr, but with a little bit of with a trick, some lattice trick, not even lattice trick, some linear algebra tricks. So it's really not, I would say it's not more difficult, at least definitely not more difficult mathematically than classical cryptography. The only problem is it's messy, and you kind of have to accept that, okay, the security of the scheme is not just based on one parameter. It's actually based on three parameters that kind of work together. So yeah, it takes a little bit of maybe a little bit of patience to get into it, but it's nothing I would say that's difficult or requires uh some additional background that students don't have. You could essentially teach lattice cryptography before teaching El Gamal and Schnorr. Of course, I would recommend maybe no, just because El Gamal and Schnorr are so easy, you learn those first, and then you learn about lattice cryptography as just some small modifications of it. But yeah, I think maybe people just find it maybe difficult because they've been exposed to the other things which are, let's say, less messy. So it's not more difficult, it's just more messy.
Yeah. And and I suppose it's a little bit like machine learning. Like the GPUs are very much focused on vector and matrix multiplications and operations and so on. Our generalized CPUs don't really do that kind of thing very well. So hopefully, when the hardware comes through that is running machine learning models, then we'll be able to run the lattice methods much better because there is a crossover between machine learning, obviously learning with errors type approaches, and with lattice methods.
Yeah, but I would say that even current CPUs are very much compatible with lattice cryptography because they do have a lot of parallelism if you
Mm.
especially use these instruction set like AVX2 and AVX512. They allow a lot of parallelism which lattice cryptography exploits. So really, we don't need a special processor that does helps with RSA, or helps with exponentiation. We really can use the chips that are already on there quite efficiently. So in some sense, linear algebra is maybe easier to do on a GPU than the exponentiation and elliptic curve operation things.
Yeah, because obviously post-quantum cryptography is breaking through, and I'll come back on to the performance of it. But homomorphic encryption still
Mm.
struggles on our traditional CPUs. But maybe we can come back to that a little bit later. So how does lattice methods work with key encapsulation? So we're moving away from the Diffie-Hellman approach of to be able to create a secret by sending public values towards and key encapsulation. So that's like the old method with the RSA. I use Alice's public key and pass my symmetric key that I want to use for the key exchange with her public key, and then she decrypts with her private key. Now, post-quantum cryptography, Kyber is coming through with a key encapsulation method. So can you just outline roughly how key encapsulation works with lattice cryptography?
So Encapsulation, the way we do it with lattice cryptography, is we first build an encryption scheme. So we don't build. So Diffie-Hellman is naturally a key encapsulation. So at CAM, you just yeah, just perfect for that. Whereas with lattice cryptography, you can't do this non-interactive CAM efficiently. So by non-interactive, I mean that both parties can just, you don't, first party does not have to wait for the other party's um, kind of message to send its own. So they just can just send the messages at the same time. So we can't do that with lattice cryptography efficiently. So what we have to utilize is an encryption scheme. And of course, once you have an encryption scheme, you just encrypt a random message, and that's your shared key. That's the high level idea. And that, I would say that's the main difference of how uh, you know that you can't just put lattice cryptography as a drop in every situation where Diffie-Hellman is used because of this non-interactive thing which we do not have
Yeah.
efficiently.
And it's probably that we'll go for some hybrid method just now because it's going to be difficult to change the TLS stack to move away from this key exchange to key encapsulation. So probably the hybrid methods will work. Okay.
Well, I think with TLS, it's not so much of a problem because it's not non-interactive. There are rounds, so there I think it works okay. But there are some scenarios where you do have some niche scenarios where you have non when you do want a non-interactive key exchange, and this is what lattices cannot do. But for TLS, I would say it's a fairly standard plugin.
That's true, yeah. TLS 1 point up to 1.2 supported RSA key exchange for the encapsulation, and then they dropped it for 1.3. So
Mhm.
you couldn't do that anymore. So I think it'll come back again when we implement this hybrid method. And when it comes to digital signatures, what is it that the lattice methods do to create a digital signature?
Mm. So there it's also in a high level, they follow the same framework that we have in the classical world. So we have one is these kind of Schnorr-like or DSA-like Fiat Shamir type signatures, where you have an identification scheme and then you make it non-interactive using Fiat Shamir. And then we also have the RSA time digital signatures, which are hash and sign. So you hash your message and then you find the preimage. So there are two ways to do classical digital signatures, and there's the same two ways to do lattice ones, but of course they are slightly different. So for the Schnorr-like Fiat Shamir approach, the most compact signatures, they are the way you do it is you have to do apply this rejection sampling trick to make distribution independent of the secret key because things you cannot mask it with a uniform mask. So in discrete log, the hard problem is just algebraic. So you want to find a pre-image, just some pre-image of the one-way function. In lattices, there's the algebraic part. You want to find the pre-image, but it also has to be short, a small norm pre-image. So it comes from particular, and this is what creates all the mess in lattices is that this requirement of the pre-image being short. And so in all the digital signatures, we have to make sure that the output is short. And so we cannot mask our secret key with a random mask like we do in Schnorr. And that then it requires some other tricks. And the kind of the issue with this rejection sampling approach that we produce a signature, but then we sometimes have to restart because that's how the algorithm works to make sure the distribution is independent of the secret key. And this creates, I don't know, some uncertainty in how in the runtime is not really consistent. So sometimes it can require no restart. Sometimes you require 10 restarts. So you sometimes so basically sometimes it's 1 millisecond, sometimes it's 10 milliseconds. In the grand scheme of things, it doesn't matter, but maybe some people, some cases you care. And then the hash and sign, there it's also the algorithms that create these pre-images are, I would say, more complicated, a lot more complicated than in the classical world, because you have to again make sure that the distribution you're generating the pre-image from is not leaking the secret key. And this is where actually, where I said for the Schnorr type signatures and the chems, you don't even need to know what a lattice is for lattice cryptography. But here, for these hash and sign signatures, that's where you really have to know about lattices, how to do this sampling well. And so that is a, let's say, more complicated signature than Schnorr. Whereas in the classical world, they're both kind of the same, complexity wise.
Yeah. And obviously the industry's been looking at zero knowledge proofs. So a lot of these
Mm,
primitives based around elliptic curve methods, pairing based cryptography seems to bring that magic in to make these things actually work. So the
mhm.
problem that we have just now is that how are we going to take all these amazing techniques for privacy and scale them into a latticed world? And I don't think we're quite there with many of
Mhm.
the primitives. I know that you've worked in zero knowledge proofs, so how might zero knowledge proofs work in a lattice world?
So zero knowledge proofs, they are, let's say, the very basic one is a digital signature. So it's the Schnorr type digital signature is a zero knowledge proof that the signer knows some secret key or something about the secret key that he's using. So that is the basic zero knowledge proof. And then we're we're building on a lot of machinery on top of it. Uh, so the one thing, so yeah, like you said, we're definitely not there yet because let's say the pairing based zero knowledge proofs and even the hash based zero knowledge proofs, there's been a lot of research. There's been a lot of work on it. Maybe a 20-year head start they've had. Whereas lattices, we really 10 years ago there was almost nothing. I would say, yeah, even like 7 years ago, there was almost nothing that was interesting. Um, kind of, but since then, a lot of people have been working on this, and something we've discovered is actually the structure of lattices has a lot of advantages over the structure of pairings. Because in pairings, for example, you do a pairing, now you're in a different group, you can't do this again, right? You're kind of stuck. Whereas lattices, you do a lattice operation, and then you basically end up in the same group, except now you have larger numbers, but okay, you just vector decompose and you're still in the same group and you can continue. So this latticey part of this, this these constructions, it's quite powerful and allows us to do zero, like it does allow us to do zero knowledge proofs. While they're not as short as pairing based ones, they are faster because lattice operations are very, very fast, these linear algebra ones. Now, there's also, in addition to pairing, there's also, like I mentioned, a lot of hash-based, zero knowledge proofs. And there's been a lot of, that has really improved dramatically, and it's really efficient. A lot of people are working on it. So this is quite an exciting field. And and I feel that lattices are competitive with that, and they should be even shorter than these hash-based. So these hash-based proofs are definitely longer than the pairing ones, but they're quantum safe. So that's the really nice part. It's hash-based zero knowledge stuff. And lattices should be shorter than hash-based. And this is something that we're working on a lot right now, try to show that by introducing lattices, we can actually improve zero knowledge proofs a lot compared to the hash-based. Okay. Right.
So obviously we started with public key encryption with the RSA method, and we're still using RSA. It's still the most popular signing method of all, and even with encryption, it's still the most popular one. But the key sizes got bigger, the computation got bigger too. Luckily, elliptic curve came along. Now Neil Koblitz created elliptic curve. It took a long time to take off, but Satoshi Nakamoto came along and showed how you could actually create cryptocurrency using the ECDSA signature. So you see a lot of companies now moving to elliptic curve. A lot of the public keys are now elliptic curve methods. So it's going to take a lot for the industry to move away from that. So can you contrast the performance that you get with lattice compared with RSA and elliptic curve methods?
Yeah. So there's been a lot of comparison done during this NIST standardization process, and also afterwards, companies IBM, even AWS, Cloudflare, Microsoft, Google, they've implemented the encryption, the lattice-based chem, and to compare what are we losing with it. So I think the conclusion is so the lattice-based chem is orders of magnitude faster than RSA and elliptic curve things stuff. Of course, it's bigger. So it's bigger than elliptic curve by another magnitude as well. So you have this, it's much faster, but it's much bigger. So if latency is an issue, it's a problem. If it's not, then doesn't. So what really the conclusion really is that it makes no difference in real life. It does not, if you use the hybrid method, it doesn't, it's barely noticeable that you're also using lattice encryption. Of course, because the size is bigger, some clients who, for example, hard coded some key sizes that they're only accepting this much, they will break. So, it'll just take, it's more of a, it's not an intrinsic problem. It's just that this is how people have coded up the way they consume cryptography. So that's something that has to change. But in terms of raw performance, encryption, lattice encryption, no, I don't see, there's zero issue. Signatures are a little worse. Signatures, you do
Yeah.
have bigger sizes, and they are somewhat slower and require more RAM. Um, so, for example, embedded devices have some problems that people have to overcome, some tricks. Also, it causes some problems with masking. So, for example, this is a real problem in the real world, where if you're using cryptography on a chip, it has to be resistant to physical attacks. And this is a completely different area now. Now that is cryptography, and people have to come up with new techniques to make these algorithms resistant to physical attacks, to probing attacks, to all these noise leakage attacks. So that's definitely where the research has to continue, and that's not a solved problem, at least from my colleagues who work in the area tell me.
Side channel analysis is very
Yeah.
difficult.
Mhm.
We use electromagnetic wave emissions and also electrical noise from the power supply. And if it's not obfuscated, especially at RSA, if you've not obfuscated the exponent type operation, then it can reveal the private key easily from that. So so when it comes to blind signatures, I know that you've worked in this area. Um, how what is a blind signature, and how, I know it's a difficult question to ask, but how might it be implemented within a lattice technique?
Yeah. So a blind signature is where basically the signer signs a message which he doesn't know, and then the verifier when the user gets the signature from the signer of his message, and this message gets revealed and verified, the signer still doesn't know when he signed this message. So this is something that David Schaum invented in the early 80s and showed that this is useful for digital money, basically, where I obtain a signature from a bank of my coin, and I can then spend it, and the bank has no idea when it signed it. So who is spending the coin?
Mhm.
And yeah, there are classical constructions from RSA, and something that we found, if you want to do it lattice-based, then you really want to use a zero knowledge proof. So basically, so it works differently than an RSA blind signature, and we can't really use the RSA idea just because the algebra does not work out. At least just for RSA, it's very special how it works. And here we can have this algebra. So the way it works, I mean, the high level is pretty simple. The user sends a blinded signature along with a zero knowledge proof that he blinded it correctly. The signer signs the whole thing, and then the user gives a zero knowledge proof that he obtained the signature from the signer. So it's basically using two zero knowledge proofs um, one to get the signature and one to present the message with the signature. So this is why zero knowledge proofs are very important in lattice cryptography, because I think a lot of primitives, lattice-based primitives more advanced than encryption and signatures, they, I would say, the most efficient or very close to the most efficient way to do it is a generic transformation using zero knowledge proof, but use zero knowledge proofs as in a black box way. So I think this is why this is why I kind of our group we spent the last 5 to 7 years really trying to optimize zero knowledge proofs from lattices, and yeah, we've made a lot of progress, but I think there's still a lot of interesting research that's left.
Yeah, yeah, that's excellent work. And many people in the industry are talking about hybrid, so we can't just switch everything off and move towards post-quantum cryptography. So it looks like Chrome is supporting
Mhm.
Kyber and ECDH. We'll also see dilithium. Well, we shouldn't really call them Kyber and dilithium anymore. We need to call them FIPS 203 and 204 and
No, they have names. It's
MLKM.
ML Chem and MLDSA now. Yeah.
Yeah, such boring names. It's really
Yeah,
unfortunate.
yeah.
I liked the Star Trek type analogy, but I suppose there might have been copyright issues
I
and
don't know how much
things.
Disney would charge for. Yeah.
Yeah, that's right. So we'd like to move towards hybrid for a short time. I think NSA is talking about 5 years to deprecate, and then I don't know between 2030 and 2035, we need to get rid of the methods completely. So how will hybrid methods work with key encapsulation and digital signatures?
So with key encapsulation, you basically, I mean, there's standard ways to do it. I'm not even sure which one they settled on, but yeah, the idea is you just, yeah, I mean, you just use both. For signatures, it's obvious, right? You just sign twice for key exchange. Yeah. So it's a similar thing. So I think hybrid is useful. Some people say, okay, we use hybrid because let's say we don't yet trust that lattices are, secure, let's say even classically. I would say it's not a great argument. I think quantumly, yes. I mean, the number of people working on quantum algorithms is so small that I think it's premature to say anything with high certainty. What is secure against quantum, what is not, right? Whereas classically, I mean, they've been around for 30 years. So I think classically they are, one should trust them. I think the issue that people have is the real issue, and that I agree with, is that implementations, right? So implementations, that's where most of the problems come in, right? So if you have an implement, if you have an implementation of just Kyber, maybe there's a problem with it. Whereas if you combine it with the EC-Diffie-Hellman, well, that's been implemented for years, so people aren't probably getting that right. So at least implementation wise, you're safer if you do the hybrid mode. But I would say that as far as, yeah, classic, being afraid that lattices are broken classically, I think that's less of a less of a worry, at least in my view. Like I said, quantumly, who knows? But quantumly, EC Diffie-Hellman has no protection at all. So it's kind of what's the yeah.
Yeah. I mean, obviously, the NIST is hedging its bets. It did all the evaluation, and
Mm.
from a security, performance, key size, lattice, won virtually all the areas, both in key encapsulation and digital signatures. But there is still a worry about learning with errors, whether it is a provable hard problem or not. So, what weaknesses do you think might come along? Maybe I'm asking the wrong question here. I think you just answered that. But is there any real worry that learning with errors will be cracked?
I mean, of course, right? I mean, I think people still worry that RSA will be cracked classically, right? So This is something we don't know. And like I said, quantum, the whole point of lattice cryptography is to be quantum secure. And this is definitely an area that has not been researched enough. And I would say lattices are definitely one of the most researched areas for quantum algorithms because that's where kind of because I would say most quant people who work with quantum algorithms are familiar with lattice problems because it kind of has made its way into quantum world because now they say we have this theorem. It has nothing to do with cryptography, assuming LWE is hard, right? So they quantumly, so they they know about lattices. What worries me a lot is what about all these other problems, right? That are okay, that are backups, right? I mean, I don't think anyone in who works on quantum algorithms even knows let's say what is Macalise? Do they know what the secret key in Macalise is, right? It's not a simple thing, right? Okay, sure, they know something about decoding linear code, but it's not a random code, right? It's a GOPA code. Has anyone worked on that? Has anyone worked in multivariate crypto, isogenies, right? So I think lattices are more established in the quantum world, but still much less than we should be comfortable with. And all these other problems, I would say almost zero, right? It's just that we don't believe quantum. There exist other quantum algorithms than the ones we know, and they don't seem to apply to these. But I think there has to be a lot more work on quantum algorithms for this quantum safe crypto. Um, so the I guess NIST, like you said, is hedging by trying to have a few different candidates based on different assumptions. But I think the question is not about hedging. The question is about how do we encourage research into those assumptions, right? This is what that needs to happen, not create a lot of new assumptions that no one is looking at. Um, but I would say the signatures part is a little bit different because uh, lattice-based signatures are kind of a good middle ground, but they're not great at, they're good at everything, but not great at anything in some sense. So now there are other algorithms that are coming around. That, for example, isogeny-based signatures are now kind of a hot topic. They are very short, but they're slow. Then there's some uh, multivariate signatures that are short and also fast, but the assumption is something brand new. And multivariate has had a history of being broken classically quite a lot. So that has to be studied. But I think there it's not there. Maybe lattices are not superior sort of by default. There are perhaps better ways to do signatures for certain for certain, if you don't care about speed, okay, maybe isogenies would be good. So there, I think the research can continue in terms of better designs. Whereas encryption, oh no, it's I think yeah, lattices are sort of better at everything. The question is, of course, security and should we have backups and how much, and we should study these backups as well. So my like if I like what I would say is not adequate is not we don't have a lot of backups, is we don't have a lot of research into the cryptanalysis of lattices or these backups. So that's what I would encourage increasing.
Yeah. So perhaps that's shown by there's only one key encapsulation public key encryption method as in Kyber, and then we've got HQC, Bike, and Macalise. I
Mhm.
mean, Macalise is so slow and the keys are massive, but it just seems to be plowing on to finally get approved. But when it comes to the digital signatures, then I think we have got our additional round two. There was many lattice that were submitted. Raccoon was one I really liked actually. It had a lot of advantages in side channel analysis and then speed. It didn't need the abort and so on, but that one was rejected. But it is multivariate and symmetric key MPC in the head that are coming through as the ones that look as if they're
That's very interesting. Yes, yes.
yeah. And I I think we'll just have to see which ones, because it was isogenies was the great hope because we could have psych, which would implement a Diffie-Hellman type method. We could drop in for that, and then it got hacked on a
Mm.
laptop over a weekend, and so
That
on.
was a
Purely
different one.
the
This one,
parameters.
I think Psyche is on a laptop in 1 second. I think
Yeah, and
but the
yeah,
interesting thing is that now that that hack was so, at first it looked bad, but now that hack is used in the signet in creating the signature. That's now the signing up. It's now,
is that
sorry,
right?
the
Yeah,
verification, right?
yeah, yeah,
So it was so efficient, this hack, that now it's used as
yeah,
part of the digital signature algorithm. So um, from the ashes, a phoenix rises, kind of
yeah,
for
yeah.
isogenies, which is a cool
Yeah,
stuff.
and it's a funny thing when you standardize. So I think Kitcha was standardized for SHA-3 and it fossilized. And then Blake, which came second or third or so on, has accelerated and way faster now. I think you get I think it's 10 kangaroos or so many, 12 kangaroos or something is the new Kitcha hash. But I think one thing that happens when you standardize is that you almost like fossilize. You can't really upgrade
Mm-hmm.
it that much. So it'll be interesting to
Mm-hmm.
see what happens with Kyber and dilithium. And obviously we have Sphinx Plus there too. Good old solid signature.
Yeah.
It's quite small keys, but obviously a bigger signature in
Mm.
there.
Yeah, but I think in the second round you have Feast, which is also based on
Yeah,
AES, and that
yeah,
I think advantage over Sphinx Plus all
yeah,
around. So that's one of these. Yeah, that's a very interesting one to watch, I would say, because it's very the assumption is AES, and it's quite efficient. So that's a good save
yeah,
that has appeared in the second round. That's quite interesting
yeah.
to
And I
me.
think there's even Ascon. So Ascon, not many people talk about the lightweight cryptography competition that NIST had, but Ascon came through because it had probably been around for a long time. There was some of these new methods that were faster, more efficient, but NIST liked that Ascon had been around for a long time. And I think it's now been adopted into post-quantum cryptography. I can't remember if it was adopted because it does hashing and symmetric key at the same time. So it's quite useful in some of these post-quantum cryptography methods as a
Well,
hashing method.
Well, we tried actually. We tried when we in lattice cryptography, like in Kyber and dilithium. Um, the most time-consuming part is the symmetric cryptography,
Mhm.
is the expansion of the key of the randomness. So, this was surprising to us. The actual linear algebra part is super fast. The main bottleneck is the hash-based stuff. So we asked NIST if instead of using SHA-3, can we use K12? Can we use
Mhm.
some, like even the designers of Ketchuk, right? They recommend
Yeah.
Ketchuk with fewer rounds, right?
Mhm.
Um,
Yeah.
or Ketchuk with kind of
Yeah.
a weekend Ketchuk. Or I'm sorry, K12 is
K12
AES.
is no K12 is the SHA-3
Is it
faster
SHA-3? Okay,
with less rounds. Yeah.
that's not okay. Yeah, okay.
12
So
kangaroos, I think it is.
yeah, exactly. Kangaroo 12 is cat check. Okay, sure.
Uh,
And yeah, getting things mixed up. And what an AES with 10 rounds, that's its own thing,
oh,
right?
that's right. Yeah.
That's
So reduced from
that's
12 down to I think it was
whatever.
yeah.
Okay. Okay. So yeah, so K12 is the SHA-3. And yeah, and we said, look, we don't even need the full strength of the, cryptographic hash. We just needed to kind of expand and look random. And they said, the designers of Ketchik said, yes, this is good, use it. And it said no. They
Yeah.
want only standardized things inside. Yeah. So I think it would be very difficult to get anything else to speed up. Yeah.
Yeah. Because I think that's what happens when you're standardizing. You're just trying to find the balance between security and performance, and
Mm.
you're just lucky. And obviously the rain down method just got it right. You had Serpent and all these other methods which maybe ramped up the security level too much,
Exactly.
and they
Exactly.
got defeated because the performance brought them down, which was quite unfortunate.
Yeah, yeah, maybe this is what you're saying about Blake and,
Yeah,
Petchuk. Like maybe
yeah,
Blake just has less, security, or they were
yeah,
more, more, yeah, more. Yeah, if you just reduce the number of rounds in Ketchuk, then
yeah,
it's as fast and as good as everything, right? So it's very, I don't know, for symmetric stuff, I don't know how they compare. I don't
yeah.
work in this area. I mean,
Um,
yeah, it's yeah, it's unclear how you would set parameters because you have no idea if having the number of rounds make things
yeah,
yeah. Whereas in public key crypto, at least I think we do have
yeah.
you know attacks that yeah do have a way to
Because
get.
most of the times we're using a pre-hash. So for post-quantum, we're not taking any size of message, feeding it in, and hashing. That would be really inefficient.
Mm,
So SHA-3 is a generalized method for squeezing data, and it takes quite a few bytes before it can actually show the efficiency. So there are better, shorter hashing methods. I forget off the top of my head, just now it begins with H. And I think it's used in one of the Sphinx Plus, where you can get really efficient hashes as a pre-hash. So you pre-hash before you actually put in to the method, and obviously it reduces the need to buffer lots of lots of lots of data. But obviously you need some trust in that pre-hash to make sure it's matching to the message. So obviously what we're doing just now is that we're taking a lot of our existing primitives and stacking them up and seeing if we can actually build them in a lattice form or a post-quantum cryptography form. Shamir has been around so long. I think early 1980s or so. It was Shamir did his shares and and created this. Well, it can be perfect security, but certainly provable security in there. And obviously, we can use Shamir in terms of distributed signatures and so on, multi-party computation. So I know we're not quite there with lattice, but how might we be moving towards a multi-party computation with lattice methods?
Yeah, that's still a bit difficult. Like for example, distributed decryption is something that it's hard with lattices to do efficiently. Threshold signatures has a bit of a breakthrough last couple of years. So I wasn't involved in it, but like two of my students were, so I'm very happy about that. That was a bit surprising to me that threshold signatures could be as efficient as they made them. Um, but yeah, there's still a lot of work left in this the multi-party setting for lattices. Um, and like I said before, I think a lot of it may again come down to let's just do a zero knowledge proof, and that's generically going to solve maybe most of these problems.
Yeah,
But that's obviously not distributed decryption. That's something else. But yeah, a lot of yeah, at least I'm trying to yeah use zero knowledge proofs in anything that that can use them. But I think yeah, also with multi-party computation, I think just the generic methods are getting so good that maybe you don't even need lattice assumptions for something that we had. We had for example. What like oblivious PRFs, oblivious pseudo-random functions, they are efficient in the classical world, not efficient in the quantum safe world, but maybe with multi-party computation or the techniques that they've developed on which like these hash functions like feast is based on, maybe that's the best way to do these oblivious some of these constructions. So we really have to re-examine and not just say, okay, we had Diffie-Hellman before, we had RSA, now let's put lattices in. You have to say, okay, look, there were other techniques before that were not as good as Diffie-Hellman and RSA, but maybe they are better than lattices, right? So let's kind of rethink about all the discarded ideas that we had before that are based on generic hatch functions, and let's think about them before we move to before we construct it out of lattices, because maybe those ideas were actually yeah, the right things to do. So yeah, you can't just say like lattices will replace everything. You have to kind of be cognizant of what else exists.
Yeah, good. And many people dream of a world of verifiable encryption, so I can make sure that that black box has actually done what it was meant to do. Because obviously anybody could write a cryptography algorithm and say that's encrypting, but there's things that are actually wrong. So, do you think we'll be able to scale verifiable encryption into a lattice world?
Yeah, I mean that's again like this is a zero knowledge proofs and it's quite efficient. So I think if you need verifiable encryption, it can be done.
Yeah,
I think that's one of the easier ones actually.
yeah. And how do you think the migration? So obviously the NSA are starting to talk about that critical national infrastructure in the US needs to migrate for the next 5 years, 2025 to 2030, and then it needs to be deprecated for the next 5 years. I think the EU is moving on this now, which is great to see. Hopefully, the UK and other countries will actually start to define their post quantum cryptography strategy. So, how do you think? It's a difficult question to ask, but how do you think this migration is there going to be some industries that will move quicker than others? What's this migration going to look like from existing public key towards post quantum cryptography?
I think you know I think people are going to drag their feet until they have to do it, and then they'll do it, right? It's like, I don't believe people say, yes, this is a very hard problem because we have to discover where the cryptography is. But, give people incentive, they will do it, right? I think we're quite good at working under pressure as a society. So, so yeah, sure. If the danger is, 10 years away, that's the way people perceive it, even though it's not true, right? That's not quite true because things that are stored now you can decrypt with a quantum computer. But let's say people are not too worried about that in most areas, and they say, look, we have bigger problems. We're not going to put all our resources on migration. But if it really has to be done in half a year, they will do it, right? This is not a science, this is a people problem, and people can rally together and do it. But of course, it'll go smoother if we start early. I always say this is like packing for vacation, right? I mean, clearly you can do it, if you have to do it, you will do it an hour before the flight. You'll probably forget some things. It'll probably be not as good. And it probably should have started a couple of days before, and it'll be a smoother process. But you will do it. I mean, you'll pack probably the essentials, and nothing horrible will happen. You'll have to maybe buy some things when you're there. So same thing with migration. If you do it now, if you start now, it'll be a nice smooth process. If you start a year before or 2 years before, you really have to. Some things will go wrong, but eventually it'll be smoothed out, right? So I'm
Yeah,
not
good.
super
Yeah.
concerned about.
Yeah, yeah. I suppose a lot of it will be around auditing and compliance, and
Yes.
to win tenders, you need to make sure that you have some post-quantum migration path and so on. It's likely to be the stick rather than the carrot. The carrot should be that you want to protect data for 10 to 20 years into the future. But obviously, the stick is more like if you're working in the banking industry, you've got to show that your distributed ledger is quantum safe in some way. So that's usually how things happen in
So with
business.
things like this, you say distributed ledger, that's a bit trickier, right? Because that's not as simple as just plugging
No,
in Kyber, right? That actually requires completely new
yeah,
technique. So that could be a problem.
yeah,
But for advanced cryptography, moving to quantum safe may not be so easy because it could be completely different.
yeah,
So there, I don't know what's going to happen.
yeah,
I guess there's not a lot of this stuff um, that's been deployed yet, so there's nothing really to switch.
yeah, yeah,
Um, but yeah, but for the basic stuff, I say yeah, it will work fine.
yeah. I mean, Google did it with Chrome. So Google
Yeah,
just said
exactly.
that we're not going to archive rate you if you don't move to HTTPS. So they moved the whole industry because most people were using Chrome. Then they forced the industry to move towards TLS underneath and have a certificate. So you worked with the inventor of learning with errors, which is quite a timeline from someone who created learn with errors, and then you co-wrote the classic paper that really uses it to create this cryptography. So what was it like working with him?
So Oded, no, he's a great guy. He's incredibly smart, but incredibly humble and kind of really. This was really so I did a postdoc in Tel Aviv. And the whole situation there is amazing, right? You have all these people who invented cryptography. You have Shafi Goldwasser there. You have Ryan Gold. You have Ali Shamir. They come to your seminars. Oded Regev, of course. And these great they come and they always just take out a notebook and are ready to take notes. So they expect to learn from you. So they really and they ask questions and kind of the great thing is like when they're not, no one there is trying to show that they're smart or anything. They're just there to learn. So it's an amazing environment. And I guess Oded was, it's kind of fit in perfectly into that environment. And yeah, so it was, yeah, very, very, let's say positive. The leadership of the field was kind of, I guess the field is defined by the top people there. And I would say cryptography was lucky that top people were so nurturing and so kind of positive and kind of concentrated on the right things at the time. So let's hope the leadership, the next generation is just as kind of inspiring as the first generation was.
Yeah. And what was your favorite research paper that you ever wrote? I know it's a bit like choosing your favorite child or something, but what was the one that you enjoyed writing most?
I would say that's the paper I wrote on with my advisor in 2006. So the first paper that we had when we showed the collision-resistant hash functions based on ideal lattices. And there it was great because nobody was working on this, and we could take our time, and it was really kind of a simple idea, but used simple math, but lots of different areas of math, and I was like really just no pressure. You just keep working on. This was before lattices was anything. No one cared about lattices. No one thought it would be practical for these worst case to average case reductions um, are something, yeah, that existed, and just theoretical kind of nonsense. But yeah, so I enjoyed working on this. It took a year and a half, but of course, it was relaxing, 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 and we got scooped at the last moment because Chris Peiker and Lon Rosen kind of had almost the same idea at the same time. But of course, it turned into a nice collaboration and things like that. But yeah, that was. I mean, I think that was my favorite time. We could really just do pure research. There's no expectations of anything. Just you're learning new things, solving new problems. Yeah, kind of
Yeah.
maybe the time I remember my PhD career actually kind of went well. Okay, yeah, up to the third year depression that everyone has, right?
There's that's
Yeah, yeah,
right.
this was
That dip that you
exactly
take in the
three
third year.
years bounce back from that depth. Yeah.
Mm. Yeah, that's good. And obviously, IBM mm, really to them patents are so important. I think they're one of the leading companies in the world for patents. But in cryptography, patents can be a bit of a difficulty. I think the RSA patent, even the Diffie-Hellman patent, the Schnorr patent, and the Shamir patent to have all caused difficulty, and it's very much a binary thing. You either love patents or hate them in
Mhm, mhm.
cryptography. So I'm not going to ask you about the downsides of patents because we all know about that. It can be difficult for small businesses to get into areas and very costly for patent fees and
Mhm.
lawyers. They make a lot of money on
Yeah.
cryptography. I can see it happening every day. So can you tell me some of the advantages that IBM would see in creating a patent and why it would be important for maybe a small business to patent their technology?
So actually, IBM has put a lot less emphasis on patents than before. So before they were
Ah,
always wanted to be number one,
yeah.
and I think lately they kind of much more relaxed about it. They don't care as much. Um, but patents and I'm not sure. I'm not sure if this is so important because IBM, at least there's no pressure in our group to create these, and because the way our research is used is really to demonstrate expertise, because IBM has a big consult, I mean, it's a consulting, a huge consulting arm, right? So the fact that a company may decide who do we hire, they say, look, all this research came from kind of organically from IBM, so there is competence there. So let us hire IBM to kind of help us. They migrate to post-quantum cryptography. But I do understand. I mean, some smaller companies, right, that start out and they say, look, I mean, we're investing all this money into research. We don't have a consulting arm. How do we, what do we do? How do we monetize anything, right? So then they justify creating patents with kind of this thing. Look, we're doing all this research where we have to patent, otherwise, how do we make money, right? So there's no blanket statement I can make about patents. Yeah. So that's I don't think I will, have one right answer that, everyone has missed in the last 50 years of debate. Right. So,
Yes. Yeah.
yeah.
Yeah. It's a difficult one, and I think
Yeah.
the Kravitz paper, the patent DSA was assigned to the US,
Mm.
to to a country. So it's possible for still to patent, but for it to still be usable. So you picked an industry path, and obviously you could be a highly successful professor somewhere in the world. So why pick industry rather than academia?
So like we said in the beginning, right? Like my day is really not that much that industrial, right? I do, like maybe you said, maybe it's almost correct that I get the best parts of research without the annoying committee work, right? Um, So, I don't feel the need to move over. And I do like solving problems that are actual problems and not something that is just there. I really hate, it's a pet peeve of mine when I
Yeah,
read grant proposals and that they work, they propose something and then they say, well, we don't know what the application is, but no one knew what the application of number theory was. And look how important that turned out. I'm like,
yeah,
okay, look, you're just
yeah,
playing the lottery here. I mean,
yeah,
you have to, so I don't, so I like more, okay, there's something in 5 years that I think needs solving. Um, and let's work on that. So,
yeah,
so in that sense, it does fit in pretty well with this medium term industry type research that IBM supports. And
yeah,
so I'm quite happy
yeah, yeah,
with,
yeah.
yeah, where I am.
I agree, and I don't think a lot of companies are investing in the 3 to 5 year window for their R&D. I think they're looking to the 1 to 3 year, which isn't going to disrupt things too much. I always think a PhD is a perfect example of creating high impact research. It's a bit of a lottery. If it works, it's amazing, and the 3 to 5 years becomes the commercialization of it. But I think the opportunity is there to build the foundation around a PhD studentship. So, what does the next decade of cryptography look like? What are the key problems that we need to solve?
Mm. So I think digitizing everything, using advanced cryptography in things like, digital currency, it doesn't have to be blockchain related, but could be even central bank digital currency. Then fully homomorphic encryption is something that's making great strides. I'm interested to see where that goes. That's definitely something worthwhile. So yeah, so I would say advanced cryptography and fully homomorphic encryption. In some sense, before security and cryptography are kind of these things that no one really cares about. They just kind of know it should be there, but it's not very exciting because it doesn't, it's the if you do sports, I would say cryptography is like stretching. It's like you have to do it, otherwise you might get hurt. But no one
Yeah,
likes, you don't do sports for the stretching. but now, with this advanced stuff, it really is taking main stage, right? This fully network encryption, people understand what it's for, right? It's it's really to keep your data. Like otherwise, you just wouldn't do some things if you couldn't keep your data private. And same thing with the central bank digital currency and this blockchain or zero knowledge for blockchain stuff. It's just things that wouldn't exist if there was no cryptography, and so it's sort of a lot more exciting, I would say, now
Yeah,
than it was before.
yeah,
So I think this is the next decade would be something like this.
yeah. Yeah, no, obviously IBM embraced the open source environment. I think with Hyperledger, they made that open source. So they've been very open with their developments. So if there was one thing you could change in your career, I I know that your career doesn't span many decades and so on, but if there's one thing you would have changed in your career, what do you think it would have been?
What would I change? Maybe I'd want to be a little bit more applied. I would more be more general. So, now when okay, I can figure out with coding some stuff I can figure out, but when I run make and it says there's an error somewhere in the Linux kernel, and it doesn't quite link correctly, I throw my hands up and look for a PhD student to help me, So this is something. This is, I think, having more general understanding of, let's say, the hardware, the operating system. This is something I wish I had as a graduate student, undergraduate student. So maybe yeah, be more generalist. So specialize in something, but also understand what's going on. So maybe this is, of course, yeah. So that's the, or maybe maybe the simple answer is just get into AI and retire. That would
Yeah.
yeah.
So my last question is, if you were a new researcher now, what problem would you focus on?
Mm, what problem would you focus on as a new researcher? I I would, I don't know. This is more of like almost an advice I would give to just general like people who do innovation, whatever. I would say, eh, you know, focus on things like before creating new things, focus on improving the things that currently exist and people are using. Because like think of what problems people have currently and like try to solve that and not create say people would be much happier if we had an app, if we had a bigger phone or a bigger or another social network. It's like, well, I don't think that makes people happier, but I think making things a little more efficient to get rid of things that people hate doing, try to solve those types of problems. This is something that I think we need as as society, right? Not just innovation, just blind innovation. In terms of cryptography, I don't know if your question was about cryptography or sort of research in general.
In
Uh,
general?
in general, yeah, I would, yeah, it's just kind of philosophical, and I would say concentrate on things that make people happier, something like that. But but like it's just yeah, not just technological progress for the sake of technological progress. Like really think about the problem you're trying to solve and try to make a positive influence. Just try to think what do people really want? Let's yeah, or maybe need, or like this would reduce people's suffering in some sense,
Yeah.
and try to work on that instead of just yeah, the next
Yeah.
step.
Yeah. I
Next,
think you'll
next
find quite a lot of cryptographers are like that. They have something else, like
problem.
people like Marty Hellman does things around nuclear weapons and so on. So I think there is that general community feel about doing good things. Like in
Okay,
digital
that's good.
identity, that's obviously an application of cryptography. Like we're looking to give identities to those who maybe don't have bank accounts and so on. So I think there's a lot of good well there in the community. My very, very last question is Zurich in Switzerland must be such a cool place to live. And you obviously moved from the US to there. Uh,
Well, I moved from
what's
France.
Oh,
To,
from France. All right. Oh,
yeah,
you've been to some
yeah, yeah.
amazing
France
countries
speaking
then.
president.
Yeah. So what is it like living in Switzerland, in Zurich?
It's, I really enjoy it. I mean, the nature is amazing. You have to make a little bit of a change. You have to have a mindset change when you move from big cities I grew up in New York, then I went to San Diego, Paris, Tel Aviv, and then you move to Zurich is I don't even live in Zurich, it's a small city, and you have to embrace nature. People, don't go to bars. You go to a mountain, you run up a mountain. You so in that, yeah, so I think it's a great environment to, let's say, raise
Yeah.
kids. So yeah, if somebody wants, sees the podcast and wants to apply to work in IBM, I mean, Zurich is a great place to apply because of Zurich.
Yeah.
That's yeah, it's a great. I'm very, very happy with the way Switzerland works. It's
Yeah.
especially when you see the way the world
Yeah.
is right now in different places. The
Yeah.
kind of the way the Swiss political system where everyone's involved is very refreshing to see, where everyone's willing to talk to each other and yeah, listen to each other. And wonderful, yeah, of course, the nature is yeah, it feels a bit
Yeah.
of a bubble here.
Yeah. That's great. Well, thank you so much for
Yeah,
spending your time. I know you must be very busy. And obviously, if you come over to Edinburgh or the UK sometime, it'd be great to have you as a guest speaker for some of our conferences and even to as an inspiration to our researchers and students. So thank you so much and enjoy the
really
rest of
say
your
thank
day.
you. Thanks,
Okay.
Bill.
Thank you.
Bye.